So welcome back, everyone. You still know me, so I'm not introducing myself again. So we were talking about learning from demonstrations, and I gave a very brief overview of maximum entropy inverse reinforcement learning. During the break, there were a few questions about are we really maximizing the uncertainty, or did you mean we are minimizing the uncertainty? And we are indeed maximizing it. So it may feel a little counterintuitive because usually you want to minimize your uncertainty in most of the applications, right? But here the idea is there are some demonstrations, and based on these demonstrations, you have these constraints. So one of the constraints is, as I said, you want to match the features of the expert demonstrations, and you don't want to introduce any new assumption, right? And the way to not introduce any new assumption is by maximizing the uncertainty. So when you maximize the uncertainty, you make your distribution kind of wide enough that it has a support in every location that satisfies the constraints. Okay, so that's the reason why we are maximizing uncertainty. So I just wanted to reiterate that. So yeah, we were talking about learning from demonstrations, and we saw this as an interesting application in many different domains. Here I have some examples for autonomous driving. So these are three different papers that all came around 6-7 years ago. But if you look at these individual papers, you'll see that they always do something on top of learning from demonstration, right? So the one in the middle, it's one of my older work. And we found that if you just combine data from different drivers and if you do learning from demonstrations from that, it may actually terribly fail, because there are some drivers who are aggressive and there are some drivers who are timid. And there are these cases in traffic where, let's say, you are trying to do an unprotected left turn. So an aggressive driver would just cut in front of the other car and just reach the other road very quickly before the blue car reach the intersection. Or a timid driver, they would just stop, look, go a little bit more, look again, right? And then they would take it slow, and maybe they would turn after the blue car. Now, when you combine the data from these two, imagine you are doing regression or interpolation between them. What happens is the car tries to do something in the middle because it's trying to be close to both of them, and then you have this case where there's actually collision, right? So we found that we need to do some data filtering first to classify the types of drivers, and then do the learning from demonstration for individual types, and then do reinforcement learning over that. Anyway, and then the paper on the right, they had to introduce a new safety filter over this policy that was learned from demonstration, because otherwise it was unsafe. The car goes out of distribution and then it does crazy things. So it was not working. But then the natural question is, why does learning from demonstration fail, right? Because as a human, when I go onto traffic, I can drive well. And maybe I'm not the best driver, but if a car drives the same way that I'm driving, I'm sure many people, many companies will be happy about it. So what is the problem? Why can't just imitate what the human is doing and get a decent driving policy? So to see this, let's try to formulate the problem again from a mathematical perspective. And here I'm going to introduce one more inverse reinforcement learning algorithm. It's called Bayesian inverse reinforcement learning. The idea is there are these demonstrations. Each of these is a trajectory. So psi1 is a trajectory, psi2 is another trajectory. So a human gave me L trajectories, right? And this data set is called dataset D. And there are some features. So this is similar to the case in maximum entropy inverse reinforcement learning. So given a trajectory, I come up with some vector of features, right? So here is one very simple example. Let's say I have this robot, and I want this robot to reach an object on the desk without colliding with this very natural-looking obstacle. The features that I can have, it can be things like final distance to the notebook, minimum distance to the obstacle, the robot's average speed, etc. And then I'm going to learn a reward function. So in maximum entropy inverse reinforcement learning, I said that for the sake of the beauty of its theory, we are going to assume the reward function is linear in features. Here I'm not going to make that assumption. I'm just going to say there is a reward function that is some arbitrary function of those features, and this function is parameterized by some w. So in this case, it can be a neural network, it can be any nonlinear function. Right? And the goal is to learn this parameters w. So how do we do this? In Bayesian inverse reinforcement learning, the idea is to do it in a Bayesian way, as the name suggests. So you create this posterior distribution, which is probability of the reward function parameters given the data set. Right? And if you can construct this posterior, later you can take its expectation, or in this case, you can find the mode of the distribution, and you can use that w as the w that you learned, or the reward function that you learned. Okay, how do we construct this posterior? Well, we use the Bayes rule. So with the Bayes rule, what we have is the posterior is proportional to the prior times the likelihood. Right? So prior is, if you have some prior information about the environment, you can put it in the prior. But like, for example, if we, let's say, we are trying to train an autonomous car, right? We talked about incorporating, people sit in different locations now. Somebody told me we can put all the traffic rules, right? So all the traffic rules would be in the prior. Right? And then there are these additional preferences or additional styles that humans drive. And that would be the part in the likelihood function, because likelihood is the term that incorporates the feedback from the human, the demonstrations, into the model. Okay, so it's the important term here. And how do we formulate it? Well, we make two assumptions. One assumption is humans' demonstrations are conditionally independent from each other. What does that mean? I have this robot system, let's say. I bring an expert to the lab. The expert controls the robot. They achieve the task. I reset the robot and I ask the expert, okay, do it again. The second demonstration that they give does not depend on the first demonstration. Right? As long as the task is the same, they are giving me independent demonstrations of the task. So this is my first assumption. Then this is how I can turn this probability over the data set into multiplication of individual demonstration probabilities. And this assumption is usually fine. And then the second assumption that I'm going to make is this is the same model as the maximum entropy inverse reinforcement learning model. It says the probability of a demonstration is proportional to the exponential of its reward. Okay? So again, this is trying to model the noisy humans, because this is saying that if a trajectory is good, it is more likely to be demonstrated by a human. It is not that, if it's not that good, it is less likely, but it is still a non-zero probability. So it is giving some slack for the human to be suboptimal. Now, the problem is, in real world, this model actually fails. Humans do not follow this Boltzmann model, right? Because, for example, here, the trajectory that I'm showing in this picture for this robot, it is actually the optimal trajectory, but it is very difficult for a human to give this demonstration because they will not be able to move this robot as smoothly as that, right? But according to this Boltzmann model, it should be the most likely trajectory. There are a few other reasons why humans are suboptimal. One of them is, as I said, it's related to the control interface. So if you are teleoperating a robot, especially if the robot has high degrees of freedom, it is very difficult for humans to control it. Think of this robot arm. So this is a 7 degree of freedom robot arm. And here, this is my former lab mate, Andy. And Andy is trying to control this robot using a keyboard. Now, to control a 7 degree of freedom robot, you need 7 continuous values. With a keyboard, first of all, you are not giving any continuous values. It's all discrete. But even if you use a PlayStation joystick, how many continuous values you are giving? It's usually 4, right? You have, is there anybody who is not familiar with a PlayStation joystick? Oh, thank God. Okay, so to think of the part of the joystick where you put your thumbs, right? So each thumb, you can move up, down, or left, right, or you can do the combinations of those. So each of these axes is 1 continuous value. So up, down is 1, left, right is 1. So you get 2 continuous values from one thumb, another 2 from the other thumb. So you have 4 continuous values. For this robot, you need 7. So you need specialized hardware, and it gets more and more difficult, especially if the human is not experienced. So it is difficult for humans to give optimal demonstrations in this case. Another interesting thing is humans have this bias about how they do things versus how they want things to be done. So you can think of this as, actually there's this experiment that they conducted at Berkeley, and the idea was they brought some people and they put them in this driving simulator, and it was like there's like a projector, they see the car's view on the projector, and they have this toy like steering wheel and like a throttle, brake, those kind of things. So they collected some demonstrations. They said, you are going to drive this car, we are going to use your data for training an autonomous car. So they collected their own demonstrations, great. And then 1 week later, they brought in the same people, they put them in the same simulator, and on the screen, they replayed their demonstrations as if it is an autonomous car. Right? And they said, yeah, we trained the autonomous car, this is how it drives, what do you think? Most of the people said the car drives a little too aggressively. It was their own demonstrations, right? And if you think about it, this makes sense because when you are driving, you have the control and you might be willing to take more risk than the case where you are in the passenger seat. Because when you are in the passenger seat, you don't have the control. If something goes wrong, your life depends on this other person. Versus when you are driving yourself, you know that you are in control and you know your own driving skills, so maybe you trust yourself and you are taking more risk. I'm not saying this is okay to do, but this is what people do. So we want things to be done in a way that is different than how we do things. So this is one problem with learning from demonstrations, because when we are controlling the robot, we are controlling it the way we are doing the task, but later we want this robot to do the task in a little different way. So there is this mismatch. So that's another problem why learning from demonstrations may fail. There are also many studies, like there is a whole Wikipedia page on different types of biases that humans have. Like here, like we studied, one of them is called cumulative prospect theory. The idea is humans are very bad at judging small probabilities. Like if you give someone a game where like they win, let's say $10 with very high probability, and then with a tiny bit probability they are losing $1 million, but if you calculate the expectation it's actually positive, they're not going to take it because it's like, yeah, what if that thing happens and I lose $1 million, right? But if you calculate the expectation, it's actually positive, so they should play it, right? And this is how like the insurance companies work, the lottery companies work, and the same thing holds true in robotics applications too. If there is like a very small probability that the robot may fail, the human actually intervenes and tries to fix it. The same thing happens on the small probability of winning something too. But anyway, this is one of the cases where like the humans take consistently suboptimal decisions when there is some stochasticity involved. So we said, okay, maybe humans are not good demonstrators. Is there any other type of feedback that we can learn from humans? And now this goes back to the discussion of like, if you remember, we said, where is the human in the reinforcement learning loop? And I said they can contribute to the reward function. And then we said, okay, I don't want human to give rewards at every time step. That is too much work. How about we do this over trajectories? So I will have a robot, and the robot is going to do something. And after watching the entire trajectory, the human is going to say, yeah, that was good. Or yeah, they're going to give some feedback. So they're going to give some reward at the end of the trajectory. This seems very intuitive, right? But it turns out this is actually not very easy for humans to do as well. And the answer may not be obvious, like why this is the case may not be obvious. But I have this like seemingly unrelated question, which is how dark is this blue? Again, in my presentations, there is no correct answer if I'm asking this to you, so just tell me something. Is that? It's light. It is? It is light blue. It is light blue, okay. Is it the lightest blue? No. Yeah, you can do it even lighter, right? So, okay, like when you say, let's say I'm trying to train a classifier of how dark a blue is. And then I show you this, you say it is light blue. So it is like, if I'm trying to do like a binary classification, indeed it would work. But if I'm trying to do regression, like how dark is this blue, because that's the question, right? How am I going to use this feedback of it is light, right? Or somebody can say like it is not that dark. Again, I don't know how to really quantify it. So there is some feedback, there is some information there, but I don't know how to convert this into like language or syntax that my robot can understand, my regression model can understand, right? And it is the same problem here, because when we show a robot trajectory to a human and when we ask how good is this trajectory, it is not that easy for the human to give feedback over an entire trajectory. Like they can say, yeah, it did the job, but not in the optimal way. Again, I need to somehow use this to train my robot, right? One way is to, of course, try to quantify it. So I can ask the human on a scale of 0 to 100, how good is this trajectory? And this person, let's say, says 78. But then another person for the same trajectory can say 56, right? So there's also going to be all these personal differences. The scale is going to be very different. So that's also going to make the learning more difficult. So we found that it is much more reliable if the feedback looks like this, right? So instead of asking which blue, how dark is this blue, if I give two blues and if I ask which blue is darker, now answering this question is much easier. And I mean, unless there is some neurological condition that I've never heard of, everybody is going to give the same response, right? So that was our idea, and like this learning comparison data. And actually, without noticing, we produce a lot of comparison data in our daily life. Like if you use Uber or Lyft, it often gives you multiple different options and you choose one of them. So it's actually comparison data. You prefer like this price, this latency, this comfort over this price, this latency, this comfort. Or like you click on a YouTube recommendation, it's a preference over the other recommended items. Or you take a route on Google, it is a preference over the other alternative routes. So we said, okay, let's do the same thing in robotics. So I'm going to show two trajectories to a human. And I'm going to ask, which trajectory do you prefer, A or B? And from their feedback, I want to learn the reward function now, right? So how would I do that? So this is my original like data with the demonstrations I was doing based in inverse reinforcement learning. Now, in addition to the demonstrations, I'm going to have comparisons. And each comparison is going to be a three-tuple. So I have one trajectory, the second trajectory, and a binary response that compares trajectory A versus B. So this is just a binary variable that's either A or B. And then I have, let's say, n of these. So I have n comparisons, right? So this is called preference comparisons. And how would I incorporate that? Now, in addition to demonstrations, I also have comparisons. Right? And one assumption I'm going to make is demonstrations and comparisons, they are independent as long as the task is the same. And each comparison is also independent from each other, again, under the same task assumption. And now the problem is, or the question is, how do we compute this? So let's look at this. It is a probability distribution over the user's response given the task, so the reward function, and two options. So I know the task, I know the first trajectory, I know the second trajectory. Now I'm trying to model the probability of user choosing A versus B. Okay? So how do I do this? There is a whole field called discrete choice theory. And in discrete choice theory, there are models for this. There are many models. I'm just going to talk about two of them. There's a Thursdonian model. What it does is it says, so this is the reward function of trajectory A, right? This is the utility of A, and this is the utility of B. It says add some Gaussian noise to both of them and compare the noisy versions, right? So why are we doing this? Because humans are not perfect. Like the true value of A might be higher than true value of B, but if they are really close to each other, the human is likely make mistakes, right? Maybe indeed 60% of the time they're going to choose the correct one, but 40% of the time they're going to choose the other one. So by adding this Gaussian noise to both of them, we kind of allow for this kind of mistakes. And this is a nice model because when you look at the probability of user choosing A over B, you end up with this equation where, like, on the left-hand side, you have the difference between two Gaussian noise terms. And on the right-hand side, this is just a constant. So what you have is just a CDF of a Gaussian, right? So this is basically saying that, let's say the trajectory B is better, right? So the difference between B and, this is the probability of choosing A. So let's say trajectory A is better. So on the right-hand side, I have a negative value because the utility of A is higher, right? And on the left-hand side, this is just a zero mean Gaussian, right? So this is what is the probability of this zero mean Gaussian being higher than this negative value. It is indeed a value that's going to be higher than 50%. Right? So this model will always, like it always makes sure that it gives more probability to the higher utility trajectory, but it allows for some noise. So this is a Thursdonian model. Another alternative that's actually more broadly used is Bradley-Terry model. And this is, again, the same softmax or Boltzmann model that maximum entropy inverse reinforcement learning was using. So it says that the probability of choosing A is proportional to the exponential of its reward. Right? And on the denominator, you have the same term for A and B, because it needs to sum up to 1. And in both of these models, this is very useful if you ever do research in this area. There are these terms that lets you adjust how noisy you think the human is, right? So here there is a sigma term. This is the amount of Gaussian noise you are adding. So if you make sigma 0, you are not adding any noise and the human is perfect. Human is always giving the accurate answer. But if you increase sigma, you are adding more and more Gaussian noise, and with high enough sigma, the utility doesn't matter anymore. So the user's choices are like almost 50-50, right? So that is like the like completely uniform random human, right? So here is the sigma term. And in the Bradley-Terry model, it is this beta term that people call it all like rationality coefficient, temperature term, Boltzmann temperature. And what it does is if beta is 0, you have 1/2 for both trajectories. So again, the human is just noisy, complete noise, right? If beta goes to infinity, then the human is rational. Whichever trajectory has higher utility, the human is always going to choose that. So it gives us this, both of these models gives us this nice like one scalar term that allows us to adjust how noisy the human is. Okay. So, okay, going back to the like how do we incorporate comparisons, now we have a way to compute this. So if we use Bradley-Terry, for example, this is what we get, right? So this is the exponential of the reward of the chosen trajectory, and on the denominator it is the chosen and the non-chosen one. Okay. And when we implement this, so here like on the left it is just demonstrations, on the right it is like one demonstration plus many comparisons. The numbers may look arbitrary, but in simulation they were giving the same learning rate, convergence rate. So that's why we chose these numbers. And the Bayesian IRL, it doesn't learn a good reward function. It thinks avoiding the obstacle is the most important thing in the world, and it just tries to keep the end effector away from the obstacle and doesn't really care about the goal. Versus when we like do the fine tuning with comparisons, or when we add these comparisons in addition, it both avoids the obstacle and also reaches the object. So this was like one simple experiment we did, but it was cool to see that with just one demonstration and 15 comparisons, we were able to learn this. And this is many years ago. Nowadays, we can do it even more efficiently. So a question that often comes up here is, here, like while talking about demonstrations, I said this model is not great because humans are not going to give demonstrations that are that good, right? There are going to be all these problems. But then here I'm also using the same model because in the demonstrations I was saying that like with this model the probability of a demonstration is proportional to the exponential of its reward, and here I'm doing the exact same thing for preferences. So why is it okay with the preferences but not okay with demonstrations? The difference is in demonstrations it is the human who controls the robot, and we suffer from all these kind of biases that humans have while controlling the robot. Versus in the case of preference, the robot is already doing something and the human is just judging them. And when the humans are judging, not controlling the robot, the amount of bias that they have or the types of bias that they suffer from is much less than the case when they're controlling the robot, right? So we are getting rid of a lot of biases, not all of them, but we are getting rid of a lot of biases that humans have. And then another question here is, of course, all these binary comparisons, like you are only asking, do you prefer A or B? Information theoretically, the most information you can get from this is 1 bit. Right? You cannot get more than 1 bit by asking A versus B kind of questions. And if you are thinking about like, okay, I'm going to train a reward function that is like a neural network and it has millions and nowadays maybe billions of parameters. like, can you really train a model with these like 1 bit of information per query? Indeed, with like small amounts, and if you are indeed like querying humans for data, it is difficult. Like most of our experiments, like here in this experiment, we made the parameter space, I think something like 10-dimensional, right? Like we are far behind millions, right? So indeed, like if you are interactively querying the human, it's going to be difficult. But there are some interesting use cases. So recently we did this work called Robometer, and the idea was to scale this idea. So we said, we have demonstrations. Like in the internet, there are like millions of expert demonstrations, right? Indeed, like we created this data set. Okay, here we go. So we created this data set. It has like 1 million trajectories over 21 robot embodiments. And most of these trajectories are expert demonstrations. So we said, okay, let's use them as demonstrations. So let's do supervised reward learning, meaning the initial frame is going to be 0 reward. Final frame is like reward 1. I'm going to interpolate the part in between. If you just learn a reward function like this, it will overfit and it will think any video that you give is just going to be this like increase from 0 to 1 increasing reward. So we had to do some tricks. One trick we did is rewinding the videos. So we were getting some parts of the videos and we were rewinding them, and then it would be like reward is increasing and then decreasing and then increasing again. So that was like one trick. But then we realized that in this 1 million trajectories, without asking humans, we can actually curate a lot of preference data. So how does that work? Because this 1 million trajectories is not just one task. There is a task of like picking up a cup, but there is also a task of stirring a pot, or there is also a task of like pushing an object from one location to other. So we said, how about something like this? I have the task like stirring the pot. Let's say that's my desired task. I have demonstrations for it. But in addition to those demonstrations, I have this like hundreds of thousands of trajectories that have nothing to do with stirring the pot. So we said, that is preference data for us, right? Because I know that this trajectory is preferred over this trajectory. And I can do this for every trajectory pair from different tasks, and I can do this for every task instruction, right? So all of a sudden, we have a lot of negative examples now, because pushing an object is a negative example for stirring the pot, or reaching an object is a negative example for stirring the pot. So that was the idea of like our scaling. So we said the preference data doesn't have to come from a human. We can just synthetically generate it in this way. And at the end, we train this reward model. Now, by the way, this is also like open source, and there's a website that you can play with it if you just Google Robometer. The idea is like you give any robot manipulation video, you write a task description, like put apple in the tray, and it labels the frames with reward values. So it says like in this frame, this was the reward, in this frame, this was the reward. Here, like the task is put apple in the tray and the video is putting apple in the tray. If you look at the top part, it indeed gives like increasing reward. But if you say the task is pick up the banana, because it's not picking up the banana, the reward stays low. And we have like a lot of different applications of this. One of them is we did like reinforcement learning with this. So here, this is a baseline. So RoboReward is like kind of concurrent work. I think it came like 2 months before we released Robometer. And they're also trying to do a generalist reward. So the idea is like you are doing reinforcement learning, but the reward function comes from this reward policy, sorry, reward model that we trained. So with this RoboReward, their model predicts like 51 success, but 45 of it is actually false positives. Only 6 of them are true success. Versus if you do Robometer, it learns to put the ping ball on the table. So I'm just gonna let it play for a while. Like initially it doesn't do it, but later it does. Of course the video is 100x, otherwise we would be here for hours. It's reinforcement learning for you. But yeah, over time, it learns to perform the task. It has higher success rate, and the nice thing is, it doesn't only have higher success rate. It only has it also has like 0 false positives. So when it predicts success, it is indeed successful. And this is important because when you have false positives, you are rewarding the agent for an unsuccessful task, and that's a very bad thing to do, because then your robot is going to learn to do that thing that is actually not achieving the task. Right. So automatic online RL was cool. We got some good rewards. So this is pi0 is our base policy, and then we fine tune it with either robo reward or robometer. We get good success rate. We also tried some like multi-stage, some sequential tasks. Like here it's put the corn in the pot and put the lid on the pot. This is all like learned with reinforcement learning, and over time it achieves the task. I'm not gonna show the entire thing. We also did offline reinforcement learning. So instead of letting the robot interact in the environment, we use all the offline data that we have, and the story is similar. And it's not just a reinforcement learning algorithm, it's also useful for like data filtering and retrieval. So one thing you can do is, let's say the task is open the red drawer, right? And the human just tells you open the red drawer and you want to do retrieval with it, meaning like you have a huge data set of robot demonstrations and you want to find the ones that are similar to opening the red drawer. One thing you can do is you can run robometer, and if the reward is increasing, if it's predicting success, you can say, okay, these are the related trajectories, and maybe you do imitation learning with those. So we did that, and we retrieved with like robometer, and these are the trajectories that robometer found to be similar to that instruction. So indeed, in all of them, it is like opening the drawer. Okay, again, some quantitative results. And later, with those retrieved trajectories, as I said, we can do some imitation learning, and it improves the success rate. So this is the trained policy. Yeah, it opens the drawer. And finally, we can use this for failure detection, because when you have a video and if the reward model is predicting success, but then it suddenly drops, you know there was a failure there, right? So we said, okay, we can use this for failure detection. Here, like there are a few videos where the robot fails, and like you see that the reward is like decreasing when the robot puts in a like places the object in the wrong position, or here, let's see. Yeah, the robot, like it gets stuck. Like it's, let's say you are doing reinforcement learning and it didn't learn to complete the folding movement yet. So you can see that the policy is getting stuck in this location, and you can see this from the reward model. And here is another one where I think it just, it's like spills the objects into incorrect location. So this is similar to wrong placement, and the reward is decreasing in that region. And yeah, I'm super excited about this project, and when we released this, it got some popularity on Twitter. So I like this a lot because this is like peer review in the wild. These are like people who are not affiliated with our paper, our university, anything. So they tried robometer on their own like robot videos. As I said, you can also do it. It's online. Like they gave their own like robot videos and tasks, and they were seeing that like this manipulation tasks, it worked. So here this is not surprising because this is similar to the manipulation works that we gave. But here's another one where like, okay, Yeet is actually affiliated with us, so this is not peer review. But the video itself is from this company. I think this is Figure, right? They have this like robot closing the dishwasher, opening the dishwasher. So here like Yeet gave the video of closing the dishwasher. And when you give the task instruction, close the dishwasher, the reward is increasing. If you say open the dishwasher, because the robot is actually not opening the dishwasher, it's actually decreasing. And then we were also impressed by some people tried things that we assume would be very out of distribution, because in the data set there is no like human mannequin or there is no human assistive task, but they gave this video and they said roll her on her side. And when the robot does this, indeed, like the reward is increasing, and like as the mannequin rolls. Right? I think there's another one like this, like lift up her legs, and when the robot does that, the success goes up and the reward is also increasing. And the same person also tried like giving this other instruction for the same video, and now the reward is not increasing and the success is always at 0. This is okay. This is my final final video of this work. This is someone from CMU, and he tried this. Like it is the, I think it's the same video. So the first instruction is this top right one. It's lift the candy bag, and the robot is lifting the. Okay, here we go. Lifting the candy bag, and as it lifts, indeed the reward increases and the success prediction also goes up, right? So the V predicts success. And later in the second video, he gave the same, in the second trial, he gave the same video, but now it said lift the candy bag without spilling. Now the thing I like about this is when the robot starts lifting it, the reward goes up, the success goes up. But when the candies, when we start seeing the candies on the table, it drops again because the instruction says without spilling, right? So here, like, it is going up, 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 but as long as you see candies, it goes down, right? Oh, sorry, this is spill some candy. So, sorry. The next one is without spilling, yeah. So it's going up, 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 and then when the candies appear, it drops. So the model was able to understand the nuance there. And there are more examples, but I'm going to skip them. So it turns out, like with the correct approach, and the preferences do not need to come from humans, and we can scale this. We can use synthetic preferences. I'm not going to talk more about preferences, but in this one final slide, I want to tell you how, like, what I'm talking about relates to RLHF. So if you are familiar with the term RLHF, it stands for reinforcement learning from human feedback. And when people think of RLHF, they automatically think of preference comparisons, because the paper in 2017, it was like an OpenAI paper, developed this term, and they were using preference comparisons. And nowadays, people are using this for the fine-tuning of LLMs, and many people actually think RLHF is an NLP term. But indeed, the original paper was doing all of their experiments in robotics domains. So in RLHF, the idea is, like, you start with a pair of trajectories, you show it to a human, and the human ranks them for you, like says this one is better than this, right? And then using this, you have a loss function and you train a reward function. So this is the same thing that I described. So everything I did with the preferences so far is this, right? We start with a pair of trajectories, we learn a reward function, later you use this reward. Actually, I did this part too. So using the reward function, you do reinforcement learning and you learn a policy, right? The only thing that I didn't talk about in this RLHF part is this closing the loop. Because using this policy that you trained, you can generate more trajectories, and with these trajectories, you collect more feedback, and you keep running this loop, right? So I think the innovation, or okay, not innovation, the nice thing about RLHF is it does this iterative improvement thing. So you are not just bound by the data that you collect in the beginning using your initial set of trajectories. Instead, you keep generating more and more data, more and more preferences, and it actually helps a lot because your policy keeps improving. Okay, so that's RLHF. So everything I talked about so far was like reinforcement learning and inverse reinforcement learning. And now I'm gonna switch gears to imitation learning. But before I do that, any questions? Yes.
Can you give like an example about the rollouts in RL, like a real world example?
Mm-hmm. So yeah, the real, like, you can think of it as like initially the robot doesn't know anything, right? So you just give an arbitrary policy, like a random policy. I mean, it's a neural network, but randomly initialized. So the robot does one random motion, another random motion, and you choose which one is better. Right? And based on this, and you do this, let's say 100 times, based on these 100 comparisons, you do the approach that I described and learn a reward function, like this Bayesian inverse reinforcement learning kind of thing, right? Now, using that reward function, you can do reinforcement learning to train a policy. Now, the new policy, maybe it's not going to do all this random motion. Maybe it will learn that instead of going to the right, I'm supposed to go to the left. So the next time, now it is not a random policy anymore. Now your policy is doing maybe this and then this, right? Again, doing like different motions every time you run, but now let's say with higher probabilities goes to the left. And now you again generate like two trajectories. You ask the human, is this better or is this better? The human responds, is this better or is this better? The human responds. You do this 100 times, and maybe when you learn the reward function again, now the robot learns that, okay, I'm supposed to go like down and left, and I need to do it in this, like, let's say, a convex motion, like a convex shape, right? So over time, like it is honing into the task, and it is learning what the actual task is. So it is the difference is like without this part that closes the loop, you are bound by the initial set of trajectories that you have, and usually your initial set of trajectories are not good for the task because you are doing random things, right? So by closing the loop, you get this iterative improvement, and it gets better and better over time. Yes.
So for the robometer paper, as far as I understand, this mainly improves the task understanding or the understanding of the language instruction, right? So it disambiguates different tasks, but it doesn't necessarily improve the performance on a single task.
Yes.
So how do we get the preferences for that? Because I imagine that's pretty difficult because you need, like you would need real-world rollouts that start from the very same condition and then you do something twice. Like how do we get these preferences?
Yeah, so it is indeed the most of the synthetic preferences that we generate are between like task 1 and task 2, and like we say if the real task is task 1, we prefer those trajectories over these ones. And among those 1 million trajectories, just a few of the data sets had also something like a classification of good trajectories, like acceptable trajectories, and bad trajectories, like failures. So we also used it for preferences, and in that case, it is indeed within the same task, right? But it is a very small amount of data set, and I don't think we did an ablation of like if we don't have it, like how much the performance changes. So there is that, but I agree that if you generate more preference data within the same task, it would be helpful. We didn't do this, but one idea is there is this paper called D-Rex, like T-Rex, but instead of T, it is D, like by Daniel Brown, Scott Niacum, et al., I'm going to say, because it's like the first author or last author, I don't remember the middle. And what they do is they inject noise into demonstrations. So let's say you have an expert demonstration. They say, like it's like state action pairs, right? They say, I'm going to keep the original demonstration and I'm going to synthesize another one where it is like state and then noisy action. And with this noisy action, you wouldn't actually reach the next state, but they ignore it. So they say, okay, this is the next state, noisy action, next state, noisy action. And then they say, this sequence is preferred over this sequence. So now you have some like within task preferences, right? And then they actually go take this even further. They say, I'm going to add little noise. I'm going to add a little more noise, a little more noise, a little more noise. So now I have full ranking, right? So in that way, you can actually, again, make it more and more efficient. It's not something we tried in Robometer, but it's an idea that exists. There's also there's a further improvement over that. I don't remember the authors, and I don't remember the name of the method, but the abbreviation is SSRR. It is the abbreviation of the method's name. I don't remember the full. I think it's like self-supervised something, reward regression, maybe? Or semi-supervised reward regression. It should be something like that. It is there are some parameters in D-Rex, and they do the tuning adaptively. So it is like the state of the art in that, like given demonstrations, how do you generate preferences kind of idea. So that would be an interesting like addition to Robometer, but we didn't try that. And the reason we didn't try that, by the way, it's difficult to work with 1 million trajectories. Like training this thing already takes days, and every trial you want to do is another couple of weeks. But yeah, that's future work. Okay. Any other questions? Yes.
Since the human time is expensive, but reinforcement learning can like do a lot of iteration, continuous and fast. How do you select the trajectories to humans?
That is a very good question that I unfortunately didn't include in this talk, but half of my PhD is on that exact question. So we have active learning methods, and the idea is I talked about entropy as a measure of uncertainty, right? Now, in this case, in active learning, the idea is you are trying to learn a reward function. Imagine you keep a probability distribution over the reward function, and now you want to minimize the uncertainty of that distribution because you are trying to go to the correct reward function as quickly as possible to minimize human time. So what you can do is you can write this as an optimization problem. such that you are going to minimize the uncertainty of the reward when the human answers a question of A versus B. So the optimization is now minimize uncertainty. Minimize uncertainty, and your optimization variable is which trajectory is to show. And we found that this is actually an optimization that is tractable, and you can solve this. So you can then ask these questions that are the most informative and minimizes the human time. I can talk more about it offline, but I didn't include it here because I thought this is maybe just a meeting, but I'm happy that you asked. Any other question? Yes.
I would assume that there's some vision language model already that you bootstrapping from, right?
Yes. So in the Robometer, we start with a VLM. It's like QN, and then we like add a reward head, and we are doing the training over that pre-trained model.
To what extent do you think there is already some 80-90% knowledge of understanding tasks in the foundation model?
Yeah. Yeah, we have an ablation on that. Without the training that we are doing, it's not that good. I think it's mainly because the VLMs, off the shelf, they are not very good at robot videos because in the wild it is mostly non-robot videos. So we have an ablation of that, and the performance improvement is actually significant. But definitely VLM contributes because the actual last example that I skip, this is okay. So somebody tried this robot is turning the knob of the oven to set a temperature, right? And I think in the original video it goes from 180 to 200. And if you give the task such that does it try somewhere? Set the oven temperature to 200. Indeed, you get an increasing reward. Or set the temperature to 180, you get decreasing because you're actually ruining it. If you say 160, while rotating, because the number changes, it goes up, but then it realizes it didn't go to correctly, it decreases. These numbers, this OCR kind of thing, it is nowhere in our data set, right? But the model is able to do that, and we know that it's because it's using this VLM backbone. So there is a lot of contribution from the VLM for sure.
So the end question is, if you were to, let's say, paint out anything to do with the robot and just observe what happens to objects, you say it's already there.
Yeah, I think
VLM could already give you good enough rewards.
Yeah, I think you can do that. You will need to do this, in painting for every frame. But if you can do that, I think you would probably get a decent reward value. That's a good one. We didn't try that because in painting is also not that efficient. All right. So next is imitation learning. So as I said, the difference between imitation learning and inverse reinforcement learning. In inverse reinforcement learning, we go for reward function versus imitation learning, we go for policy. And the vanilla imitation learning algorithm is this idea called behavioral cloning, and it's a very old idea from 1988. You have expert demonstrations. Expert demonstrations look like state action pairs, right? In this state, expert took this action. In this state, expert took this action. So what you can do with it is, given a state, you need to predict the action. It is a supervised learning problem. So that is what behavioral cloning does, right? Given a state, you put a neural network, you predict the expert action. And then you have a very clear loss function that is the difference between your predicted action and the expert action. And so this is behavioral cloning. And after so many years, this is still the first thing that people try because it is so easy to implement. And with enough data, it actually works well. But of course, it has some problems like the compounding errors problem. So the idea, again, you have an environment, you get demonstrations, you do supervised learning, you get learned policy, right? The problem is with the, because you are approximating the policy with a neural network, the robot is at state S, and the expert took action A, right? Go from this S to this A. Now, when a neural network approximates this action, it is going to be, instead of from this S to with this A, it is going to be a slightly different A. It is going to move from here instead of here. Right? Now, when you go here, now you are in a state that was never in the data set, but it is close to a state that was in a data set. But because of this little difference, your neural network may make a slightly bigger error. And now you are also going a little off, a little off, a little off. Over time, you are deviating from the original trajectory so much that you are in a state that is completely different from what the robot has seen in the data set. So now it's going to go completely off track. Right? So this is the compounding error problem. And direct policy learning is like an approach, or it's like an interactive approach where you try to solve this. The idea is like you collect some demonstrations, that's your training data, you do supervised learning. You, with the policy, you roll out it in the environment, and using this rollouts, you collect more expert demonstrations. So for example, there is this famous algorithm called DAGGER, data set aggregation. The way it works is you initially do your basic imitation learning, the behavioral cloning, right? But later, instead of directly deploying it, you say, I'm going to create rollout, so I'm going to let the policy run in the environment, but with some, let's say, 10% probability at every time step, I'm going to pause the system, and I'm going to ask the human to give a demonstration from that state, right? So in this way, even if the robot starts deviating from the original path, the human can bring it back to the original track, and then the robot will learn how to get back to track. Okay. And as I said, this is like this behavioral cloning or this imitation learning. Like it was very popular, and then at some point reinforced, like people thought, oh, there are so many problems, these compounding error problems, the reinforcement learning is the way. But like increasingly now people are going back to imitation learning because again it's very simple, and what you can do is you can start with these like VLMs, like these pre-trained models, and you can do behavioral cloning, like you can add an action head and you can do behavioral cloning on that, and you get pretty good results, right? Like this physical intelligence company, for example, they're collecting their own data, and they like do this imitation learning kind of approach. I mean, they do a bunch of things, but imitation learning is one of them, where they get a good VLA. But then there's the question of like, do we have enough data? So here, this is a visualization by actually a person at Physical Intelligence, where they tried to compare. This is like 2 years old, so nowadays it might be a little different, but I don't think the idea changes. They tried to compare the robot data we have with the data that went into LLM or VLM training. And this is the visualization. So here, like that is GPT-2. It's already an old model. And here, this is like Llama 3. This huge thing that I cannot even know, like this looks almost straight, right? And this is OpenX embodiment. That is like the public data set. That's like very large, very large. And this is the Pi data that they collected in-house. So we have, compared to like language and vision, we have very little data. And I would also argue that robotics is more difficult because it is a higher dimensional problem. Like language is one dimensional in the sense that it's just, you're predicting the next word, right? For the next word, there are like, okay, thousands of options, but it is still like one dimension at a time. Versus if you are controlling a humanoid robot, let's say, now at every time step, you need to predict if like more than 100 continuous values. So the dimensionality is much higher. So and the amount of data we have is very little. So the community is going for this approach where like with whatever data that we have, we are going to do some pre-training in the factory, and then we are going to deploy the robot. And in this deployment environment, humans are going to control the robot for some time. And with this, we are going to fine-tune the pre-trained model, and it's going to be specialized in that target task, right? And these are some like screenshots from papers that are, you know, kind of famous papers and that try to do this. And like if you look at these, as few as 100 demonstrations, or a small target domain data set with around 100 trajectories. I find it a little funny that like all these papers, I think except the last one, they use these adjectives to make it sound small. But now I'm imagining like, okay, what is the use case of this? Like imagine a company trains a robot in the factory, and then they deploy, I'm imagining like they deploy this robot to my grandmother's house, and now my grandmother is supposed to teleoperate this robot as few as 100 times to make it like fill the dishwasher or something, right? Like that's not happening. I mean, my grandmother didn't, like she never even touched a keyboard in her life. And then I'm questioning like, yeah, teleoperation is difficult. There are some works that try to make it like teleoperation from like non-expert humans or constrained demonstrations. And I also talked about like learning from preferences. That is like an easier interface. But these feel very like unnatural to me, because like when is the last time you teleoperated your friend or you give preference feedback to teach a task? Right, like that's not how humans teach things to other humans. I mean, again, as an engineer, it's fine. You can teleoperate a robot, you can teach things that way. But when we are talking about like everyday people, teleoperation is not a concept in their life. Or like this preference feedback, they can understand it, and sometimes we use it, but it's very uncommon, right? Versus like when we are teaching each other, we either talk, like I give instructions, right? Or I do the task myself with my own hands, and the learner observes it and learns from it. And so that would be much more natural, and that is the kind of like imitation learning or learning from human feedback that I want to go for. So instead of like learning from teleoperation, I want humans to talk to robots, or I want humans to do the task themselves, and then the robot is going to learn from it. So how do we do this? And this is the part like where my lab is currently focusing on. So for example, for learning from language, we said, well, instead of preference data, we could actually convert the feedback that comes in language into preference data. So it is like, instead of a human watching two trajectories and saying this one is better, if the human watches one trajectory and says like move faster, now I should be able to extract the preference data from this, because I know that the faster version of the same trajectory is preferred over the original trajectory, right? So that's automatically preference data for me. And this is much more natural. So how do we do this? We train this latent space. So this is like, this is the same idea as in machine translation. So in machine translation, I guess there's this old idea that, let's say you have the same sentence in English, in Turkish, in Greek, in Vietnamese, like there are these different languages, right? It's the same sentence. What you do is you train an encoder for every language. And the goal is to map the sentence into an embedding space such that as long as the sentence is the same, you get the same embedding from different languages, right? From different encoders. And this latent space is now shared between all the languages, and you will have decoders for different language. So if you want to translate from English to Turkish, now you can do like English encoding and then Turkish decoding, and you get the translation. So here the idea is the same, but instead of different languages, now we have trajectories and language feedback. So let's say I have trajectory A and I have trajectory B, and I have some label that says trajectory B moves faster than trajectory A, right? So I'm going to encode the trajectories into some latent space, and I'm also going to encode the language into some latent space, and I'm going to align them. How do I do that? Well, I know that the difference between B and A is described by this language, so I'm going to align the difference with the language embedding. Right, so that was the idea. That is how we trained the latent space, and we checked if there is like this alignment between the language and the trajectory pairs. Indeed, there was. And this, just for visualization, the latent space looks like this. I mean, of course, in reality, this is like 768 dimensional thing, but here I'm just doing 2 dimensions. Like every trajectory is a point in this latent space, and every like comparative language feedback is a vector, right? Because when the user says like this moves faster than this, I'm taking the difference between these 2 points, which is like a vector, and that feedback corresponds to that vector. Now, why is this useful? We can use this in multiple different ways, but I'm going to show 2 of them. For example, I can start with a trajectory, so the robot shows a trajectory, and then the human says something like move slower. I can move in the direction of move slower. I can try to find a trajectory in that region. I show it to the user, and the user says move closer to the bottle. We move in that direction, and so on. Right? When we implemented this in simulation, it was indeed like getting increased reward. It wasn't reaching the optimal. And the reason is it is a memoryless type of feedback. So when you say move faster, and then later when you say move more smoothly, it completely forgets about move faster, and there is a chance that you create these loops within the latent space, right? So the second way is actually better, and it's closer to the preference-based learning that I was talking about. So when the user says move lower, you find that imaginary trajectory in that latent space, so there is this latent point, right? And you can learn a reward function over the latent space, right? So because I know that the user prefers this imaginary trajectory, this point in the latent space, over the original point. So now I have preference data in the latent space, meaning I can learn a reward function over the latent space. And this is actually not the end of the story, because, we add this to the preference data set, because we never told the user to give feedback about, let's say, the height of the robot. Right? Like we didn't say, should it move lower or higher? We just said, give feedback to this robot. And they intentionally chose to give feedback about the height of the robot, like should it move lower or higher? So we should be able to model this as well. And the way we do this is, or the way I think about this is, the user could say, move faster. The user could say, move further away from the stove, right? There are all these things they could say. And among these, they chose to say move lower. So what this tells me is I have this discrete options of feedback that I could give, and I chose this one. And this is like, again, discrete choice, right? This is like, I am choosing this, not over just lower and higher, but over these many options. And that is actually more informative feedback because now I can say that there are these counterfactual feedback, the feedback the human didn't give, and the human prefers what they said over these counterfactual ones as well. So I have many more preference data. Right. So when we implemented this, it improves the data efficiency further, like with this implicit feedback. We implemented this on a real robot task, on like a little kitchen setup. So people were just typing their feedback, and then the robot was improving based on that. The humans like it, and we also recorded the time it takes for humans to give feedback. So here the blue is the regular preference data, orange is the new one with the comparative language, and orange is faster, but this is actually not giving the full picture because we asked humans to type their feedback. Instead, like if we had a speech to text, it would be faster. And we were not expecting this because when we were developing the method, we were always trying things like move lower, move faster, etc. But some people really like to give feedback. Like, do you see this? Somebody was typing for 3 minutes to the robot. So there are some outliers, but with speech to text, this would be even faster. So this is like one way we can do or we do learning with language feedback. Another type of feedback is the human's own demonstrations. So one interesting idea is, I can actually talk about this RoboClip real quick. There's this model called Clip, right? Let me start with this. Oops, not this, sorry. This was by, I believe, OpenAI in 2021. They developed this model called Clip, and the idea is you have an image encoder, you have a text encoder. If the text caption belongs to the image, you want the dot product between the embeddings to be high. Otherwise, it needs to be low. Okay, so you are doing this contrasted training, and at the end, these encoders learn to map the image or the text into the same point if they are like semantically the same, or if that caption belongs to the image. Right? So we said we can do something similar for training robots because this clip idea, it doesn't have to be between text and image. It could also be between text and videos. Right? There is this data set called How to 100M, so it has like, again, millions of videos, and we can learn this embedding such that if the caption belongs to the text, they're going to map to the same latent point. And how do we use this as a reward? Well, the idea is, so this is our standard control loop, right? We have the policy, environment, state, action, and let's say I have some demonstration. I'm going to map this demonstration into the latent space, And whatever my policy does in the environment, I'm also going to map it to the latent space. And I'm going to check if these two embeddings are similar or not. So I'll simply check the dot product between them. And if it is high, that is high reward for my robot. If it is low reward for my robot. And at the end, we get this behavior where like, this is my PhD student opening a little door in the lab. And this is the video that we give. Now we know that with the way that we trained the clip model, or this video clip model was trained, this opening the door motion will map to a point in the latent space that is where the text embedding of opening the door would map into, right? So now if I use this video to generate the rewards, I actually get a behavior like this where the robot is also opening the door, because both of these would map to the same point. They are both opening a door, right? So with one demonstration, we were able to learn this. And then we realized, oh, this generalizes well. So we were having some fun with it. Instead of giving real videos, we started giving animations, and it still works fine. Here's another one. So this is the reinforcement learning way of doing it. There's also the imitation learning way of doing it, which is this other hand me the data paper. So it's like a human is doing the task, and now we want to imitate it, right? What we did is we track the hand of the human. So like in the video, we track their hand motion, and we say, let's say we have some offline data set of robot demonstration. So this is like OpenX embodiment or like some large data set, right? So first, we do some filtering based on the scene. So if it's like a kitchen scene, we want to get the kitchen scenes from the dataset. If it's like a toilet, we get the toilet from the dataset. So we kind of make sure the environment is similar. After this visual similarity, we do the tracking of the human hand using Molmo. So it's like it points at the center of the hand, and then we use co-tracker to track it. And we do the same thing for the robot's end effector in the dataset, those like filtered trajectories, right? And later, among those filtered scenes, like we said, if it is kitchen, we want to get the kitchen ones, right? We find the trajectories that are most similar to the human's hand motion. Like the robot is doing something similar to the hand motion in terms of just these tracking results, right? And later, we just use these most similar ones to do imitation learning. Right? So we do the imitation learning in the robot embodiment because we don't want to deal with embodiment gap. It is just the tracking that we care about. If the human hand motion is the same as the robot hand motion, we say, okay, this is the same task. We are going to use it as an expert demonstration on the robot side, and we do imitation learning with it. These are like some real-world results. And I think I have a full video of, let me just quickly go there. There are some baseline comparisons, but yeah, here we go. So this is like, we have a full video as well, but I don't think it's in the slides. Like the human collects one hand demonstration, and then he goes to the machine and like he clicks enter. The machine does all these like retrieval, filtering, retrieval, and still not correct. Filtering, tracking, retrieval, imitation learning process. It takes something like 2 minutes, and after that we have the evaluation, which again takes something like 15 seconds. So in like under 3 minutes, we were able to learn these tasks from like one human demonstration. Okay. So that is all I have for the imitation learning part, and I have, I think, 3 minutes left. In these 3 minutes, so I'm gonna very briefly talk about the first tutorial in the afternoon. I think is Boroe here, or maybe, oh, he's there. He's there, and just in case, I also have his photo. So he's going to be leading the tutorial. It's going to be about learning from human interventions, and I want to give like a general picture of like what I talked about today. So it doesn't capture everything I talk about today, but like when we were talking about learning from demonstrations, I mentioned this maximum entropy inverse reinforcement learning, right? And I said it relies on this assumption that the human demonstrations come from this model. So what are we doing here? This is like, given the task, what is the probability that the human gives this demonstration? So we are trying to model the human's feedback, or we are trying to model the human's data. So this is for demonstrations. And then for comparisons, we said, like to learn from comparisons, we need this model, right? And it was, what was this? Given the task and the questions, what is the probability that humans answers this way or this other way? Right? So again, we are trying to model the human feedback, and here, like I talked about Thurstonian model or the Bradley-Terry model. And finally, while talking about comparative language, I said, like, how do I, like the user said, move lower, right? How do I use this feedback? And the idea was there were these many different options that they could, many different feedback options they could give, and they chose to give move lower, and I can map this into a preference. Again, the idea is how do I model the probability of humans giving this feedback over all the other feedback types that they could give. So in general, I believe that most of the efficient robot learning from human feedback algorithms, we achieve them when we model the human's feedback well. So if you are trying to learn from humans' eye gaze, maybe you should first question, can I model the human's eye gaze? Or if you are trying to learn from humans' hand gestures, maybe you should think of can I model how the humans make hand gestures to the robots, right? So the first tutorial in the afternoon is going to be about learning from interventions. And the idea is the robot is going to be doing some task, and whenever you want, you can intervene the robot and you can take over control. You can fix its trajectory, and over time it's supposed to learn from this. Now, if this is your task, how would you approach this task? Like, how would you model the human's intervention, right? So here there is one little difference from what I talked about so far, which is the robot-gated versus human-gated. Everything I talked about so far is robot-gated, meaning the robot asks a question and waits for the answer. So it is the robot that decides when to get feedback from the human. That's why it's called robot-gated. The other, but in intervention learning, it is human-gated, meaning the human is watching the robot, and when the human thinks it is going to make a mistake, the human takes over. So it is the human who decides when the robot gets feedback. So it may look very different, but the human-gated is actually just one step further than robot-gated, because you can convert the human-gated feedback into robot-gated feedback with one step, which is you can assume that it is robot-gated, and at every time step, the robot is asking the human, do you want to give feedback or not? Do you want to give feedback? If the human doesn't intervene, the answer is no, you move on. Do you want to give feedback? No, you move on. When the human intervenes, now the answer is yes, and there is this additional feedback, which is, okay, I'm going to take this action, right? So you can think of it as robot-gated in this way, and the idea is, now it's robot-gated. Yeah, if a human is able to intervene a system at will, when they intervene and how they intervene it become important, and they carry important information about the desired policy. So the tutorial is going to be about trying different models on this. The idea is if you have a robot policy, and if you have a mental model of the human, so you are kind of predicting what the human would do, how do you use these distributions to predict if the human is going to intervene or not, or how the human is going to intervene if they're going to intervene, right? So maybe during the lunch or something, you can try to think of it a little bit ahead of the tutorial. So it's if this is the human action, if this is the robot action, is the human going to intervene? Because things that you should think of is even if these two actions are different, it doesn't necessarily mean the human is going to intervene, because maybe the robot's action is good enough, right? It's not the same action, but if it is close enough, it's fine. The human is not going to intervene. So maybe brainstorm it a little bit, and then in the tutorial, I think end of the tutorial, we are also we have a paper on this, so the answer is already on the internet. But I think Borway also has an implementation that you can work on, and you can see it in action in the robot. That's all I have for today. So thank you very much.